Hello, a great welcome to the series on PLAXIS. Myself Jaraj and P. This is tutorial number 2 and provides the bearing capacity analysis of a circular footing. This tutorial is very similar to tutorial 1 except that in this case the foundation is taken to some depth, that is the actual depth of excavation, and the foundation will be modeled as a plate element facility available in a PLAXIS. So let us go straight to the problem statement. So as you can see, the footing that will be analyzed here will be a circular footing that is of diameter 2 meters, that is the radius will be 2 by 2, that is 1 meter. And in this case, the depth of excavation or the supporting level of the foundation is taken as 1 meter. And we shall use an axis symmetry model for this problem because as you can see that is symmetrical about both x and y axis. And in the plan, the soil domain that is considered is of dimension 4 meter by 4 meter, and the depth of or the extent of the soil profile up to the bedrock is 4 meters. So the soil parameters that will be used for the tutorial will be, we shall use a Moore-Coulomb material model, and the drainage type will be drained because we'll be considering the water table level at the bottom of this layer, and the unit weight in the saturated and unsaturated condition will be taken as 18 and 16 kN per meter cube. Regarding the stiffness parameters, the Young's modulus of elasticity will be taken as 5 into 10 raised to 3 kN per meter square with a Poisson's ratio of 0.25. Now coming to the strength parameters, the quotient will see for the clay soil will be taken as 5 kN per meter square with an associated friction angle of phi is equal to 22 degrees and a direction angle psi is equal to 0 degrees. Now coming to the footing parameters, because we'll be modeling the footing also in the PLAXIS, and the corresponding material parameters for the footing will be, we shall use the type as the plates, and the material model will be a linear isotropic behavior, and then the unit weight will be taken as 10 kN per meter cube. The thickness of the footing will be considered as 0.5 meters, and the E value of the concrete, that is the material for the foundation, will be taken as 2.5 into 10 raised to 7 kN per meter square with an associated Poisson ratio of 0.15. So let us start the PLAXIS. Okay, fine. So let us start the new project. So the title of the project, let us fill up. So it's a bearing capacity analysis of a circular footing. Okay, so we have filled up the title. So if you want to insert any comments, you can fill it. So let us now add the model parameters. So the default units shown on the left side will be accepted as it is. And let us now fill the limits of the contour. X min will be 0 and the X max that will be taken as 4 meters. And coming to the Y, it will be Y min will be 0 and Y max again will be 0. It will be, sorry, it will be 4. So that's okay. So we have filled up the contour limits. Now let us straight away proceed to define the soil stratigraphy, which will be done through the boreholes. So we shall create a borehole. So let me just place the borehole over here. So let us create a soil layer. As we know that in this present case, we have only one soil layer. So we'll add one soil layer. And let us first fill up the extents. The top will be 0 and the bottom will be, it is a 4 meter deep, so it will be minus 4 meters. And right now we can see that the free water head that is at the soil surface, we want to take it to the bottom of the soil layer. So let us accordingly fill this head as minus 4. Okay, so you can see that yes, it is taken to the bottom of the profile. So now let us proceed to define the materials. So straight away we have the material option over here. So let us just press materials button. So as you can see that we want to create the soil property. So we shall use the set type as the soil and interfaces. So let us press the new button. So we shall use the name of the profile as clay. The material model will be Moore-Coulomb. It will be a drained analysis. And coming to the unsaturated and saturated weight, we shall use 16. For example, unsaturated we can use it as 16, and the saturated we can use it as 18. 18. Okay, fine. And we don't want to fill up any advanced parameters over here. We can go to the parameters wherein we will be able to fill the stiffness as well as the strength parameters. And in this case, the Young's modulus of elasticity will be taken as 5000 kN per meter square and the Poisson's ratio, it will be taken as, say, 0.25. So we'll use it as a 0.25. And then we have so as you can see that once we fill the E and new value, it automatically calculates the values of the G as well as the odometer modulus. Now let us fill the strength parameters. The quotient will be taken as a 5 kPa, that's 5 kN per meter square, and the phi value will be taken as 22 degrees, and the dilatancy in this case will be taken as 0, and so you can see that based on these values, the PLAXIS automatically calculates the values of the shear as well as the longitudinal wave velocities, right? So we don't want to specify any variation of the stiffness across the depth of the profile using the advanced parameters in this case. So this means that this is okay for us. We have defined all the properties, so we can press OK button. Now, as you can see that yes, the soil layer with a name of clay is defined. Now we need to assign this clay material to this borehole. So what we need to do is that we need to simply drag and drop over this. You can see that yes, the layer of the soil, it is the color, it is changed to the blue. So this means that a proper material known as a clay is assigned to this borehole. So this is okay for us. So once this is done, so this is okay for us, fine. So finally we obtain the the 3D soil model with the material assigned to it. And as shown here, you can see that this is the borehole that we have placed in the model. So we can just use here the reset zoom button in order to see the full model. Okay, fine. Once we have defined the soil stratigraphy, material, the extent of the soil profile, next we can proceed for the modeling of the footing. So for which we'll be going straight to the structures mode. So in this case, as I already told, we'll be modeling the footing using the plate option in the PLAXIS, and this foundation will be placed at a depth of 1 meter below the ground surface. So obviously, as it is an axisymmetric problem, instead of the circular footing, we'll be using 1/4 of a circle as the footing shape. So let us proceed for first developing the footing. So for this, we will systematically follow a procedure. First, we shall develop a polyline, and for the polyline, we will develop the plate surface, and then we shall extrude this plate surface in order to develop a 1/4 of a circle cylinder, and then we shall remove the surfaces, explore the surfaces like that. So let us first proceed for the development of the uh, plate using the polycurve option. So first let us define the polycurve. So as you can see that yes, so we'll just start from this point. Okay, so we shall go to the segments. So we shall add the various segments. In this case, remember, we'll have one radius segment along the axis one, that is of 1 meter radius, and then another segment of 1 meter along the y-axis, and then we have got a circular segment. So let us start adding all these things. So here, as you can see that we have already added one segment automatically by default, which is of length 1 meter. So this is acceptable to us. So just add it. Okay. Now let us go to segment 2. In segment 2, as you can see that we would like to add a arc. So you can see that obviously here this arc is not acceptable. We want to have it. This means that we can go with a segmental angle of. So let me just cap it as segmental angle. So relative start angle, let us keep it as, for example, here it is a 90. Okay, that must be good enough for us. Yes, and so here we can see that the radius of this arc, it is set as 1 meters. So this is acceptable to us. So now we need to develop a line corresponding to the vertical one. So let's just add one more. And in this case, obviously, we know that this should be again a straight line segment, and its length will be 0. And the radius at the start, let's keep it as 90. So let us see. Yes, you can see that we have completed the polyline, which essentially represents 1/4. And remember, a polyline segment is composed of line segments, right? So this is okay for us. So as you can see that if you just zoom it, you can see that yes, we have constructed a polyline. Now what we shall do is we will convert this polyline into a surface. So what we can do is that we can just right click on this polyline, and if you right click on this polyline, you will get an option create surface. So just click it. So you can see that yes, A surface is created that represents 1/4 of a circle, and remember this surface is a circular having a radius of 1 meter. Now what we shall do is that we shall extrude this surface. So we started from polylines, we created a surface. Now we shall proceed for extruding. Okay, this is surface. Okay, up to the depth of the excavation. So what we can do is that we can straight away go to this option, that's the extrude object. So press this. Okay, so you can see that yes, as you can see that right now this is extruded upwards by 1 meters. We want to extrude it downwards. So what we can do is we can just provide it as a extrusion vector. Okay, this is one only, so we can provide the z as -1. It's -1. So you can say that yes, it is extruded down. So this is applied. Okay, so we can see that right now we have extruded this surface up to the foundation level. As you can see, this is a single entity. So before creating a surface at -1, let us first decompose this solid volume into surfaces. So just right click on this. So you can see that here there's an option decompose into surfaces. So now let us start deleting the various surfaces that we have. Okay, so we can see that now we have generated a surface at 30 to -1 meters. So now let us just convert this surface into a plate. So right click on this, so we can create a plate. Fine, so you can see that now a plate is created at 30 to -1. So now let us, we want to define the properties of the plate and assign to this area, right? So let us go back to the materials over here, right? And here, as we want to create a structural element, we need to select the correct set type. So if you go down, you will find that there's an option called plates. Select it. Okay, so now let's start a new material. So we'll call it as, for example, this is my footing. Okay, it's my footing, and the thickness of the footing will be set as a 0.5 meters. 0.5 meters, and the unit weight will be 10 kilonewton per meter cube, and we shall set it as a linear, and click the box against the isotropic. Okay, so now let us start providing the e-value. So the e-value that will be used for this analysis will be 25E6. So 25E6. Okay, so the Poisson's ratio, you can see that E1 is equal to E2, and we knew that the Poisson's ratio will define as 0.15. So that's all about the definition of the properties of the material for the plate. So this is okay for us. So now okay, so now let us just right click on this area, and if you see the plate, you will find that we can, there's an option called the set material. We'll set it as the footing material. Okay, so as you can see that yes, the material footing is assigned to this plate at z equal to -1. So this means that we have completed all the modeling requirements. Now we are ready to proceed to the mesh. So go to the mesh. So now as you can see that here when you go into the mesh, so we'll just set it into laser zoom. You'll find that yes, the entire soil model is visible here. We are unable to see, okay, the surface at z equal to -1. So what we can do is we can go to the model explorer here. The best way is that you go to the geometry, and in the geometry you will find that there is a soil volumes option, and the soil options you will find that yes, there are two volumes over here. So if you just keep one off, you'll find that yes, this is, so if, let me just zoom this a little bit. Okay, so you can find that yes, this is the, okay, the surface that we have just created, which represents the footing at z equal to -1. You can just rotate this view also for more clarity. Okay, fine. So see, this is what we have created. So now let us proceed for the meshing activity. Here we have two things. We know that this is a plate element. This is a heavily loaded one, which is subjected to displacement loading. So we need to mesh this a little bit more finer. Then we can adopt a medium course for the balance portion. So let's just select it. If you select it, you will find that yes, there's a fineness factor of 0.5. I want to keep it to much finer, say 0.25. So what we can do is that we can refine the mesh over here, and you can just press it. So this is now, you can see that there's a 0.35. Again press it, you will find that it's a 0.25. So that's okay for us. So this means that this plate is now uh, subjected to a fineness factor of 0.25. Now we can proceed for the meshing of the balanced region. So we can go to the generate mesh option. So here for the global meshing, we are using an element distribution of medium. So press OK. Fine, you can see that the meshing is in progress. So we can also view the generated mesh with the PLAXIS. And if we are satisfied, from there we can directly switch over to the stage construction stage, where we'll be able to define all the stages for the construction, and then proceed for the numerical analysis. So let us just wait. Okay, yes, I think that the meshing operation is complete. Let's do the mesh. Okay, fantastic. Okay, yes, so let us see the mesh. Okay, you can see that yes, here is the mesh. Now here again we are finding that okay, that particular portion is not available to us. Again, as usual, what we did in the earlier case, we will go over here, go to the soil volumes and go to the temperature volumes and keep this opaque. Okay, so here you will find, let me just zoom this a particular portion. Okay, so okay, this is okay for me. Now let me just zoom this particular portion. You will find here now that the plate element, okay, it is being given assigned a very finer measure compared to the surrounding soil. This is very much required because this is a very heavily loaded area, right? So okay, fine, so we are happy with the meshing fineness and the coarseness adopted by the PLAXIS. So this means that we can now apply the loading or the prescribed displacement. So we have to go back to the structures mode in order to assign the so-called surface displacement. So let us just right click on it. So here there's an option called create a surface prescribed displacement. Okay, fine. So here we can see the surface prescribed displacement, what it is. So okay, the x and the y direction will assume the free boundary condition, and it has set the prescribed condition. And here I would like to use lesser one, minus 0. We'll take this footing to an elastoplastic condition by subjecting it to a prescribed displacement of say 400 mm, that is minus 0.4 meters. So that's good enough. So let me just save this model again. So this means we are now ready to move on to the staged construction. Okay, in the stage construction, we are ready to define the various stages. So if you see the initial phase, so you can just see the initial phase. Obviously, we know that in the initial phase, the entire soil volume should be active because our objective is to calculate the stresses in the soil due to the surface of the soil. So if you go over here in the initial phase, you'll find that yes, we need to keep this volume on. Okay, so that's good enough. Soil volume, and okay, that's good enough for us for the initial phase. So let me just reset the zone. So this is a model for the initial phase. You find that the plates are not activated, surface displacements are not activated here, right? And also you will find that the excavation is also not activated. So if you double click this, you find that yes, that's the phase 1, and the calculation type is set to be K0 procedure, wherein we will use the Japanese formula. So the other options we can keep the default is okay for us. So let us add one more phase, and this phase, as you can see, that this is tagged as phase 1, and here we want to create or simulate the so-called excavation for a depth of say 1 meter. So what we need to do is that we can go to the soil. Okay, we can remove rather than soil, we have to go to the, okay, in just a minute. So we have the geometry, yes, and we have the soil volume. And the soil volume, what we can do is that we can make this off. So here you will find that yes, this represents the model explorer in phase 1, wherein a particular soil portion in this area is removed, representing excavation, and still you will find that the plates are inactive and the surface displacements are also not activated here. So if you double click this, you'll find that yes, the calculation type is plastic, and I don't want to change any numerical control parameters here. I'll just keep it okay. Now, so this means that phase one, which represents the excavation, is complete. I want to add one more phase, which represents the construction of the foundation. And here, what I would like to do is that I would like to activate the plate element here in this phase. So you can say that yes, the plate is now available here, which represents a condition wherein the foundation is constructed. If you just double click here, you can find that the calculation type is plastic, and all other parameters we want to keep the same. This is okay. Now let us create the most important one, wherein we are going to apply the prescribed displacement. So we add one more. So here you will find that our intention is to apply the surface displacement. So you can keep the surface displacement on here, right? And now if you double click this, you'll find that yes, the calculation type is a plastic. Here I want to increase the number of steps here. If you see here the numerical control parameters, you'll find that the PLAXIS has used. If I go for the default iteration parameters, the maximum steps allowed is 250, but here I want to change it to a little bit larger one, that is 1,000 steps, because that will be required to take the displacement to say 0.4 meters. So I just uncheck this. So this means that I can change this maximum steps to say instead of 250,000. So this is okay for me. All other parameters I will keep the same. So this means that I am now ready with all the four phases, including the initial, to proceed with the calculation. So you can see that the calculations are in progress. So once the calculation is complete, we will review the the results through the post-processor mode. And so let us start proceeding inspecting the various results. So as a good practice, it's better that we straight away start from the initial phase. So you can see that this phase one, yes, the initial phase is selected. And let us just go and inspect the distribution of vertical stresses. So I would like to have the Cartesian stresses sigma set. Yes, you can see that yes, as expected, we can see that the stresses increase from the top to the bottom, and this is the kind of the linear stress distribution, which means that the calculations are proceeding in the right direction. Having done that, we can straight away move to the very critical one, that is now phase 3, and let us start inspecting the distribution of the deformation. So we'll go for the phase displacements and use it. So this is how the distribution. So let me just rotate this. Okay, you can find that this is the distribution of the deformations. As we can see that the maximum deformation of 400 mm around, it is reached at the lower surface, and we can see that the deformation contours okay, goes on decreasing in the downward direction as expected. So we can also go for the curves also. That means just to see the behavior of the point that represents the center point of the footing, and this point was already selected by us. Okay, so let us go straight to the curves manager. So if you go to the curves manager, so we have the two things. That is, first of all, let us see the curve point that was already selected, and probably I think that this is not covered in the presentation. And as you can see that the curve for which the details will be inspected is the point A, which corresponds to z equal to -1. Okay, that is 0, 0, -1. Okay, that is good enough for us. Let us go to the charts. Okay, so new, and we can go for the force, and we can have it as fz here, and we can go to the point A, and we can inspect the deformation, that is the total displacements, use it. So this is okay for us. So this is how the load deformation curve looks like, and we can also just make it in the way in which we want. What I will do is that I will exchange the axis. So I want the deformation on the y-axis. I will flip horizontal and the vertical. It's okay. Fine. So this is how the load deformation curve is. As you can see that the maximum value of the deformation is 400 mm, and the corresponding value of the load is around, I think that is a 334. So if you press this point, you'll be getting the corresponding the point on this curve. So that works out to be 334 kilonewton, and accordingly the computed ultimate bearing capacity at this displacement of zero point 0.4 will be 334 divided by the area. Please remember we have to use the area corresponding to 1/4 of the circle, which is pi by 4 into 1 squared, and this ultimate bearing pressure happens to be 425 kilonewton per meter square. If you apply a factor of 2.5, we arrive at a safe bearing capacity from the shear criteria as 170 kilonewton per meter square. On the other hand, if we assume that the tolerable settlement of the structure is of the order of say 50 mm, we find that the corresponding ultimate load works out to be say 100 kilonewton, which will be converted into an allowable bearing pressure of 127. Which means that for this particular foundation, it is a settlement of 50 mm which governs the design, and we shall adopt a corresponding safe bearing capacity of 127 kilonewton per meter square. So that's all for this video. See you. Bye.